So we went through the basics of complex numbers, right? Dealing with the imaginary unit I and the various powers of I, how they cycle through I, -1, negative I, and 1, and then back to I. And now we're just going to get into the basic operations, adding, subtracting, multiplying, and dividing of complex numbers. So adding and subtracting is very simple. It's just essentially combining like terms, like you would do with polynomials. You're really just combining the real parts and combining the imaginary parts separately. So the first one I give you here is -4 plus 6i, right? That's one complex number, plus 8 minus 3i, that's the second complex number. So you're adding them together. So what you're going to do is you're just going to add the -4 and the 8, which are the real parts, and then combine the 6i and the -3i, which are the imaginary parts. Combining the real parts is going to give you 4. Combining the imaginary parts is going to give you 3i. So you end up with 4 plus 3i. Now, as with polynomial subtraction and pretty much any kind of subtraction, when you're subtracting, what you do is you think of subtracting as addition of the opposite. So I was subtracting -2i plus, I was subtracting -2 plus 5i, which is really adding 2 minus 5i. And now it's just an addition problem, like my previous one, where I would just combine the reals and combine the imaginaries. So I would end up with 5 for the reals and then -7i for the imaginaries. So 5 minus 7i would be my result. Now, one little interesting thing to note is you can, in fact, add or subtract imaginary numbers and get back a real number, right? These are two imaginary numbers, -2 plus 6i and -5 minus 6i. But what happens when I add them? The real parts are going to combine to give me -7, but the imaginary parts are 6i and -6i, so they're just going to cancel out and become essentially 0i, but 0i is really just 0, so this is just -7. So what did I do? I added two imaginary numbers and got back a real number, right? Which is something that you might not think you'd be able to do, but yes, you can. You can add two imaginaries to get a real. All right, now multiplication is a little bit more complicated because, yes, it's going to be like a FOIL problem, but there's a little bit more to it. All right, so you started off just like it's a FOIL problem where you say, all right, well, 2 minus 3i times -1 plus 2i. I do f, which is 2 times -1, so I get -2. Then I do o, right, so that's my f. Then I do my o, which is 2 times 2i, which is 4i. Then I do my I, which is -3i times -1, which is plus 3i. And then I do my L, which is -3i times 2i, which is -6i squared. So that's my L, right? -6i squared. And now what I do is, normally I'm used to this. When I FOIL like binomials, for example, a lot of times the O and the I, the middle terms, combine, and they do here also. So in this case, 4i and 3i combine to give you 7i. But now look what else happens here. Since I squared equals -1, -6i squared is really -6 times -1, which is really +6. So that L is actually a +6. So not only do the two middle terms combine, also the first and the last terms combined. So -2 plus 6 is going to give me 4, and then my result would be 4 plus 7i. All right, so that's really the thing that you have to keep in mind with the multiplication of the imaginary numbers. you're going to actually get two pairs of terms that are going to combine. So the middle terms will combine, but also the first and the last terms will combine, because you're just using the fact that I squared equals -1, right? So really what ends up happening, whenever you have something like this, some number with an I squared multiplied by it, it just changes the sign, right? Because multiplied by -1 changes the sign. So -6I squared became +6, right? If I had +3I squared, it would become -3, so on and so forth. All right? So one little other kind of multiplication that's of note is if you multiply a imaginary number by what's known as its complex conjugate. Now what's the complex conjugate of a plus bi? It would just be a minus bi. So conjugates have the form a plus bi and a minus bi, right? So those are going to be conjugates. You keep the real part the same and you just take the opposite of the imaginary part. So those would be complex conjugates. So what I'm doing here is I'm multiplying complex conjugates. And you'll see what's interesting here that happens is when I multiply the first terms, I get 9. Then I do the outside ones, that's -9i. The inside ones would be +9i. And then the last ones would actually be -9i squared. So you can see the O and the I here are just going to cancel out their opposites. But what happens with the F and the L is, remember what we just said, when you do -9i squared, it changes the sign because it's multiplying by -1, so it becomes +9. So this is really 9 plus 9, which is 18. So what's interesting, another thing here that you did, is when you multiply the complex conjugate of an imaginary number by that imaginary number, you're going to end up with a real number. So you can, again, turn an imaginary number into a real number by multiplying by its conjugate, right? By its complex conjugate. And that concept is what comes into play with the division, right? So when we're dividing complex numbers, we're not actually dividing really, like traditional division. We're actually multiplying the numerator and denominator by the conjugate of the denominator. So what it's kind of similar to is when you would try to rationalize the denominator, like you would multiply the numerator and denominator by like radical 2 or something like that to get a radical 2 out of the denominator, or you would even multiply by conjugates to get radicals out of the denominator. But here we're multiplying by the complex conjugate to get the imaginary number out of the denominator. So rather than call this rationalizing the denominator, what I like to call it is realizing the denominator. Because what are you trying to do? You're trying to turn the denominator into a real number, right? Because once you turn the denominator into a single real number, then you can just use your distributive property to divide both terms of the numerator by that denominator, right? So I like to call it realizing. Nobody ever finds that funny, but I find it interesting. I find it funny calling it realizing, right? But whenever I say it in class, nobody seems to think it's interesting. So, but realizing the denominator, that's my phrase for it. All right, so if I was going to divide 2 plus I by -4 plus 2I, again, what people try to do sometimes, they say, oh, I can divide 2 by -4 and I by 2I or something like that. You're not doing that. What you're doing is you're treating this like you're trying to realize the denominator. And how do you realize the denominator? You multiply by the conjugate of the denominator. So if you have -4 plus 2I, the conjugate of that is going to be -4 minus 2I. But again, since you do it to the denominator, you got to also do it to the numerator, because you're multiplying by a form of 1 then, which would be legal, right? So what happens here now is the numerator is going to be, a standard multiplication problem. So 2 times -4 is -8. 2 times -2I is -4I. I times -4 is -4I again. And I times -2I is going to be -2I squared. And now the denominator is going to be a little bit nicer, right? So negative 4 times negative 4 is 16. The O is negative 4 times negative 2i, which is positive 8i. The I is 2i times negative 4, which is negative 8i. And then the L is 2i times negative 2i, which is negative 4i squared. So what happens in the numerator? Negative 4i and negative 4i give you negative 8i. And remember, negative 2i squared is really positive 2, changes the sign. And in the denominator, this is what we wanted to happen. The imaginary parts cancel. So we just have 16 plus 4, right? Because negative 4i squared is positive 4. And now we're almost there. So the numerator is negative 8 plus 2, which is negative 6, minus 8i. And the denominator is just 20. And you could make the argument that you could leave it like that, but usually what they ask you to do is they ask you to write it in the standard form, which is a plus bi. So what you really want to do here is use the distributive property. So write this as negative 6 over 20 minus 8i over 20, right? It's like, think of it as like the distributive property with division, right? You're dividing both pieces by 20. And then each of these pieces, though, in this case, is going to reduce a little bit. Negative 6/20 would be negative 3/10. And then negative 8i over 20 is going to be negative 2/5 I. So that would be your standard a plus bi form, right? Where a is negative 3/10 and b is negative 2/5. So that would be your normal form, your standard form. Now, rather than have to always go through this process, what you can do is you can kind of memorize what happens when you multiply an imaginary number by its conjugate. What's always going to happen when you multiply a plus bi times a minus bi? You're just going to end up with a squared minus b squared I squared, right? Because bi times negative bi is going to be negative b squared I squared. But again, recall what happens when you multiply by I squared, it just changes the sign. So you end up with a squared plus b squared. So this is actually an interesting thing, because what is a squared plus b squared? It's something that in the second unit we said didn't factor, right? It's the sum of squares. And in the second unit we had said that the sum of squares does not factor. But actually it doesn't factor just with real numbers. It would actually factor with complex numbers, right? So the sum of squares actually does factor into a plus bi times a minus bi. But in this case, really what's more important for us is realizing the reverse. If we multiply a plus bi times a minus bi, we always end up with a squared plus b squared. And you can see how that applied up here, right? When I did negative 4 plus 2i times negative 4 minus 2i, a was 4 and b was 2. So what did I end up with? I ended up with a squared, which was 16, plus b squared, which was 4, right? Because a was 4, b was 2. Well, a was negative 4, and b was 2, right? So I ended up with negative 4 squared, which was 16, plus 2 squared, which is 4. So 16 plus 4 gave me 20. So if you remember that a squared plus b squared, it can just save you a little bit of time when you're dividing the complex numbers. All right. So that was just pretty straightforward. That was just your adding, subtracting, and multiplying and dividing of complex numbers.